Good afternoon, everyone. Welcome to the latest edition of the QSimFP Seminar. I'm Chris Goodwin. I will be your chair for today's session. A quick announcement before we get started this afternoon. So this is the penultimate session of the series before we break the summer. The final session will be held on the 18th of June, and then we will return after the summer break on the 17th of September. I will remind everyone again at the end of the session, just in case we have a few late arrivals. So today we have Dr. Sam Dolan from the University of Sheffield. Sam is the senior lecturer in applied mathematics. His research interests include black hole perturbation theory, gravitational wave astronomy, modeling extreme mass ratio in spirals with gravitational self-forces, superradiant instabilities of black holes, and analog gravity. Today, Sam is going to be taking us through a talk entitled The Maxwell Fisheye Lens, Perfect Focusing, and Collapsing Spheres in General Relativity. So without further ado, Sam, it is over to you.
Thank you, Chris, and thank you to the organizers. I appreciate the invite to speak. I'm just going to assume that you can hear me okay, and press on. Thank you. Okay. So my aim in this talk is to link a few ideas together in the spirit of analog gravity and quantum simulators. So I'm going to start with some motivation coming from thinking about gravitational lensing, and then show how that links up with the old idea of the Maxwell fisheye lens for perfect focusing in optics. Then I want to get on to thinking about physical spacetimes and how they might relate back to the Maxwell fisheye lens once we understand that the perfect focusing is coming from the fact that there's a spherical geometry associated with this lens. So we're going to be using conformal symmetry. We're going to be leaning into that to make some of these links. In the fifth section, I'd like to propose a neutron star analog. Basically, if you can build a physical system with a refractive index of a certain radial profile, then you can claim that it's recreating some of the physics in lensing in a neutron star. That's what I will say at this point. And then I'm going to go on to think about dynamical situations, dust balls collapsing or balls with pressure collapsing under their own gravity. And I'm going to try to link this back to the Maxwell fisheye lens. So I'm not sure if any of this is truly original. The part which might be the most original is this. And if you have any background reading or references for me, I'll be very grateful to hear them at the end. So to motivate, let's start with a picture here of some compact body with a gravitational field. And I'm going to allow null geodesics, so rays or light rays, to pass through this body. And because of the gravitational field, they're being, the rays are moving together. And if this is a particularly dense body, like a neutron star, then neighboring rays will eventually meet. And they meet at a cusp caustic, that's here where the red dashed lines meet. And you can see beyond that region, we've got more than one ray passing through each point. Now let's think about some wave fronts that are being pulled along those null geodesics or light rays. We've got three of them here. And the parts that pass through the body, so deeper into the potential well, they're retarded, they're kind of held back until eventually a cusp forms in the wave fronts. And in fact, it's a pair of cusps. And the pair of cusps then travel along the dashed caustic as shown. Okay, so now we've turned basically one wavefront into something with a more interesting structure. So if we were waiting downstream, we could now in principle see the same wavefront 3 times passing by us. Okay, so that's an example of a cusp caustic, and it arises very naturally all the time anywhere where we've got some kind of slowing down in a wavefront. With some colleagues in Nottingham and elsewhere, so with Theo Torres, Max Lloyd, and Silke Weinfurtner, we began to think about waves passing over submerged islands, where if the depth of the water decreases, the wave speed slows down, and so you get some kind of analogous effect. And we found that by changing the depth, or changing the profile of the island, we could go from having a single cusp in the caustic into something that looks more like a butterfly caustic here with 3 different exterior points. And by changing the profile, we could kind of move that butterfly down to a point, so to get more intense focusing happening. So then a natural question is it possible, or under what circumstances, can we get perfect focusing, where not just neighboring rays cross, but a much larger bundle of rays cross? So in thinking about this, I very quickly realized that I should go back and back in the literature. And I also had a very helpful email interaction with a professor in Japan, Professor Okubu, and he encouraged me to start looking at gradient index lenses in optics. So a gradient index lens is a lens whose refractive index is varying smoothly with radius. And here is an example. This is the Lundberg lens, and it takes initially parallel rays and it focuses them at a point on the far rim of the lens, as shown. So I would call this perfect focusing, because it's not just the neighboring rays that are being focused there, but all of the rays that enter the lens. But it's in fact not the Lundberg lens I'm going to be looking at today, but an even older idea that goes back to 1853. So in 1853, a curious problem appeared in the Dublin and Cambridge Mathematical Journal. The reader was challenged to find an optical refractive medium such that all the rays proceeding from any point in the medium will meet again accurately at another point, and such that the path of every ray in the medium is a segment of a circle. Okay. Well, in 1854, the solution was posted in the same journal, and the anonymous question setter remarked that the possibility of the existence of a medium of this kind possessing remarkable optical properties was suggested by the contemplation of the structure of the crystalline lens in fish. So that's how it gets its name, because 11 years later, this solution appeared in the scientific papers of James Clerk Maxwell. So we now know that it was he who posed and solved that problem, and he was also interested in eyes of fish. Okay, so that's enough history. Let's get on to how it looks. If we have a refractive index that varies with radius in exactly this manner, then rays that emanate from a point on the rim of the lens will be focused back at the opposite point on the rim of the lens, as shown here. So we could look at this point on the left, and we can see that those rays that stay inside the lens are focused at the point on the right. So this was a nice toy problem of its age. And we can extend it a little further. We can think about wave fronts. So the wave fronts here would be orthogonal to the rays, and they would look like the colored lines here. So initially circles around the point, and then becoming straight lines, and then back to circles again inside the lens. And we can also think about an extended version of this lens, where instead of the lens covering just a circle, it now covers the whole of space. And in this extended version, if we start with a point source anywhere, the rays are eventually focused back to another point, and it would be the antipodal point in this sense. So there's a reciprocal relationship here, and it's a point on the opposite side of the origin. So yes, this is hinting at some geometry, because we're getting focusing wherever we start at some antipodal point. I can also draw the wave fronts associated with these rays, with the picture on the right here. And in fact, the rays and wave fronts in an extended fisheye lens form Apollonian circles. So this is geometry going back to the Greeks. And you can see that the wave fronts and the rays cross at right angles at every point in that square, and they form nested circles, which, yeah, are not quite symmetric, but they're clearly nested. So this is all very nice, but how should we better understand what's happening here? Is there a natural geometrical reimagining of the fisheye lens? Well, like all the questions I'm posing rhetorically, the answer is yes. And the way to do it is to map the rays on the plane to rays on the surface of a sphere, because we know that the great arcs on a sphere, whatever point they start at, great arcs will go out and meet again at the antipodal point on the sphere. So perfect focusing is perfectly natural on a sphere, and it looks more miraculous on the plane. So to make that a bit more precise, we can map between points on the plane. So the plane here is the black horizontal line. We can map them onto a sphere by taking the point on the plane, running a line to the south pole of the sphere, and then extending that line until it meets the sphere again. And that then defines an angle chi in blue here. So there's a geometrical way to go from points on the plane to points on the sphere, and the coordinate transformation is given here. It involves the tangent of chi over 2. So there's a map between rays in the lens and arcs on a sphere, and those arcs are, of course, geodesics. And in a moment, we'll be going to space-time, and these will then be the null geodesics of a curved geometry, a sphere. So again, adding a little bit more detail to this, we could, so if we want to think about the rays in a lens, a good starting point is an action principle, and specifically Fermat's principle of least time. So the path between 2 points is that which takes the least time. And in our optical medium, we have a varying refractive index, and that's the speed in the medium divided by the speed of light. Okay, so we can now rewrite this involving a refractive index and an element of length here. And then we can make a reinterpretation that this element here is in fact the element of length on a curved space-time, so a Riemannian space. And then the metric on that space is simply the flat space metric multiplied by the square of the refractive index. Okay, so we've moved from a flat space to a curved space just by multiplying by some conformal factor here. Okay, so in this way, we can map naturally between the null geodesics on space-time and the rays in a lens. And specifically for Maxwell's fisheye lens, the refractive index, all the way back here somewhere, takes this form, this particular form. And now we're thinking about a geometry where that's a conformal factor, and I've written the flat space element here in polar coordinates. Now, making this coordinate transformation here, this becomes the line element for a hypersphere. So this is manifestly the line element for a hypersphere, and that's revealed by the geometrically motivated coordinate transformation. So now it becomes obvious why we're getting this perfect focusing happening. It's because we can map directly to great arcs on a sphere. Okay, so we've seen here the link between Maxwell fisheye lens and the sphere. Now, a sphere is a perfectly natural geometrical object, and it arises all over the place when we think about general relativity and curved spacetimes. So in the remainder of this talk, I'd like to now think about curved spacetimes that take a very particular form, basically the form of a hypersphere with this line element, put together with time in the most trivial way, but then multiplied by some conformal factor here, omega hat. And we need the conformal factor to be non-zero everywhere and positive. And I'm going to say that any such spacetime, well, it's conformal to the hypersphere, and therefore it's conformal to the Maxwell fisheye lens because of the way that the rays will be focused. Why can I say that? It's because conformally related spacetimes share the same null geodesics. Okay, I'll make that slightly more precise in a moment. But if I want to think about dynamical situations, such as balls collapsing, then I need to allow for dynamics here somewhere. So I'm going to allow this conformal factor to be a function of space and time, so that we can have dynamical situations. Okay, so let me now try to make this statement a little more precise. Let's consider two spacetimes which are related by conformal factor. So the metric of one is equal to conformal factor squared times the metric of the other. I can then make some statements. So this is recapping what's well known, but to certain literature, but maybe not to everybody. Firstly, null geodesics. If we have a null geodesic on S, then we straight away have a null geodesic on S tilde. They share the same null geodesics. Spacetime symmetries. If we have a conformal killing vector field on S, then we straight away have a conformal killing vector field on S tilde. And you can see this quickly by thinking about the Lie derivative. That means if we have an affinely parameterized null geodesic and we contract the tangent vector with the conformal killing vector field, then we get a constant of motion along the null geodesic. So there are nice relationships when it comes to frequencies and so on, coming from just from the geometry. Now we come to fields. For scalar fields, if the field satisfies a conformally coupled scalar field equation, then on one spacetime, then it does so on the other spacetime too, with some straightforward relationship between the fields just involving the conformal factor, or some power of the conformal factor. And finally, or not quite finally, we can think about fields of higher spin like electromagnetic fields. If we have a Faraday tensor on one spacetime, then we also have a solution. Now, let me say that more precisely. If we have Faraday tensor that satisfies the source-free Maxwell equations on S, then straight away we have a Maxwell field that satisfies the source-free Maxwell equations on S tilde as well. And note here that the indices must be downstairs in this relationship for it to be as written. And finally, for gravitational fields, we know that the Weyl tensor, which is also sometimes called the conformal tensor, that it takes the same form on the two spacetimes with its components related as so. So there's a whole bunch of relationships between conformally related spacetimes. What that means in practical terms is that we can take nice simple solutions on a sphere, like for Green's functions or for fields or whatever we need, and we can then map those onto this kind of more general class that's conformally related. And that means we can start to set little projects related to, for example, looking at Hawking radiation or whatever you're interested in on more physical spacetimes, if you can relate them back to spheres and back to the Maxwell fisheye lens. So let's now shift our attention to what we're calling physical spacetimes. So now we want spacetimes that satisfy the Einstein field equations, as written there, for some physically reasonable energy momentum or stress energy tensors, which must, of course, be divergence-free. So we can ask a nice simple question. Are there any physical spacetimes that are conformal to Maxwell's fisheye lens? And again, the answer is yes. So a well-known example would be in cosmology, the Friedmann spacetime. But I'm not going to start with that because that's very obviously related to a hypersphere. I'd like to start with one that perhaps is underappreciated, that it actually relates to a hypersphere and to the Maxwell fisheye lens. And that's the interior Schwarzschild solution. So in 1916, Carl Schwarzschild presented his interior solution for a star that is a spherically symmetric, incompressible ball of fluid of uniform density mu and mass m. And he presented this quite shortly after presenting his exterior solution, which is the one that probably you're more familiar with, the metric that describes it describes the spacetime outside any spherically symmetric matter distribution, and it also describes a spherically symmetric black hole. That's the exterior solution. Here I'm talking about the interior solution, but you can match the two together at the surface of this star or ball. So the way, if you've seen this before, you've probably seen it in Schwarzschild coordinates. This is the way it typically appears in textbooks, involving two functions of radius that look like this. And okay, it's not too complicated to write down, but it's not obvious geometrically what's going on here. What we do know is that when you calculate the stress energy tensor and you read off the diagonal components, you get the density and the pressure. And the pressure is some function of radius. And on the surface of the sphere, the pressure is 0. So this condition determines the radius of the sphere. So you can construct these solutions of any radius you like up to some limit. If you try to make it too compact, things go wrong. And specifically, they go wrong at the Buchdahl bound. We can make spheres no more compact than a radius of 9m over 4, so 2.25 m. And what goes wrong? Well, as we approach that limit, the pressure in the center of the star diverges. So we can interpret that as a singularity developing in the solution. Okay, so that's the interior Schwarzschild solution as typically presented, but there's a more geometrical way to think about it that I would argue has been underappreciated for a century. Right. Before I move on to that, I just want to show one plot here, and this plot is showing the TT component of the metric against the radial coordinate, and we can see that depending on the density of the star, we can match the interior and exterior together, and more dilute stars, the lapse or the GTT stays quite close to 1, but as we approach the Buchdahl bound, GTT can get down to 0 in that critical case. So we've got deeper potential wells for more compact stars. Okay, but now I want to come to my main point. The interior solution can also be written in in isotropic coordinates. Okay, where instead of r, we're now using rho, the isotropic radial coordinate. And the first person in the literature to look at this form that I know of was Wyman in 1946. He started with the line element in this form with some conformal factor and some refractive index. Well, actually, he didn't quite write it like this, but he had two free functions and a flat element here. Okay, so going to this paper and reading off what he derived, there are explicit expressions for the conformal factor and for the effective refractive index. And note that the refractive index here is some constant term multiplied by the refractive index of the Maxwell fisheye lens we saw earlier on. In a moment, I will define this curly r. Okay. So in isotropic coordinates, the radius of the star is a, but there's a nice simple relationship between the isotropic radius and the radius in Schwarzschild coordinates. And you can have it either way around. Okay. So this way of writing the solution is getting us closer to the understanding that what we have here is a hypersphere spatial geometry. So again, we make the coordinate transformation to write this in hyperspherical form multiplied by conformal factor. Okay, so we can write down everything in closed form. It's got an effective radius of r hat, which is this constant factor multiplied by the curly r, and the curly r, which governs the extent of the hypersphere relative to the isotropic coordinates, is defined here. Okay, so now we come to an interesting question. How much of the sphere in the conformally related geometry, how much of that sphere is inside the physical sphere of the star? And what you would expect, or at least what I would expect, would be that very dilute stars would not have very much lensing happening, but very compact stars could have extreme lensing occur. So to quantify this, we should think about the value of chi, this angle going from naught potentially up to pi, to think about its value at the surface of the star. And its value is given here. So now we can think about some interesting special cases. When can we get perfect focusing? Well, to get perfect focusing of null geodesics inside this hypersphere, we need at least half of the sphere to be represented. To go from one rim to the other rim on the Maxwell fisheye lens, we need to go across one of the hemispheres of the sphere. In other words, we need chi naught to be at least pi over 2 for perfect focusing. And intuitively, we wouldn't expect perfect focusing until that star has shrunk inside the light ring at 3m. And that is actually what pops out of these equations. If we have a star of exactly 3m in radius, then chi naught from this formula is pi by 2. And if we approach the Buchdahl limit, the Buchdahl bound, that's r of 9 over 4m, then a goes to m, and chi naught goes to pi. So that's the situation where we're getting the whole of the conformal sphere in there. But this sphere is now kind of somehow pinching itself off from the rest of the universe. So you would expect that to be a singular or at least problematic case. But that case corresponds to the extended Maxwell fisheye lens. Okay. So in this model, you can't get to that point, but you can approach it. Okay. And then what would be happening inside the star is the rays would be being focused, and they would have to pass through a very narrow throat to escape from the star. Okay. So I guess this is where we make contact with the simulators community or the analog gravity community. If you can build a physical system, it could be in optics, or it could be in condensed matter, or it could even be waves in a wave tank. But if you can build a system which has an effective refractive index, then you can build a lowest order approximation to a neutron star for the purposes of lensing. Okay, and all you need to do is make your refractive index look like this, where inside some radius, it takes this form, and outside the radius, it takes this form. And here's a plot to show that all this means is a nice, smoothly varying refractive index that tends to 1 in the far field. And then depending on the compactness of the star you want to model, it reaches either quite small values of like 1.5 or quite large values of up to around 6 or above. So depending on what material you have available, perhaps you can do this. And I think it would be interesting and worthwhile to do because you could, make some more interesting connections between different parts of physics. Okay, now, quite recently I found that actually other people are on this trail, which is great. In this paper, they didn't start with the Wyman solution, but instead they used transformation optics to go from the Schwarzschild-like form to the isotropic form. And so there are other people already thinking about, analogues to star-type systems in optics. Okay, now I want to come to the part that, I expect that this stuff about the interior Schwarzschild solution has been rediscovered more than once. But now I'd like to come to thinking about some work that I've been trying to do recently, to think about in which cases the Maxwell fisheye lens, despite being a static solution, can still describe dynamical situations of collapse or expansion of spheres in general relativity. So again, I'll ask, is Maxwell's fisheye lens of any relevance to collapse scenarios? And I would argue, yes. And it clearly is, because we can go to the oldest and one of the nicest models of collapse due to Oppenheimer and Snyder. Oppenheimer and Snyder considered a shrinking ball of dust of 0 pressure and uniform density throughout that ball. And they embedded that into Schwarzschild spacetime. And their interior metric was simply a Friedmann spacetime with a hyperspherical geometry multiplied by some scale factor. And introducing a conformal time, you can then write that as a conformal factor multiplied by geometry of the kind we've been considering. And what they did was, by embedding that dust ball into Schwarzschild spacetime, they then derive from the matching conditions that the surface of the dust ball follows a radial geodesic in Schwarzschild spacetime, and that drops out of the matching. So this is a well-known model that's clearly conformally related to a hypersphere, and so its lensing should resemble the Maxwell fisheye lens. So now we've got 2 cases. We've thought about the Schwarzschild interior with its uniform density and the constant acceleration of the surface. So there's some pressure that's resisting collapse. But here we've got Oppenheimer-Snyder collapse, where we've got uniform density through the sphere, but 0 proper acceleration of the surface. In other words, nothing is resisting collapse, and the surface is following a radial geodesic with 0 proper acceleration. So now we ask the question, are these 2 well-known spacetimes part of some larger family of spacetimes of uniform density? And again, the answer appears to be yes. So to look into this, I kind of rooted around in the literature until I came across a model that suited my purposes. And that was the model of Narii and Tomita from 1968. And so with just a little bit of rewriting, their model looks like this. We've got some conformal factor here, which depends on time and radius. And then we've got an effective refractive index here, which again depends on time and radius. And then we've got some expressions, okay? I just want to highlight that the refractive index, again, has a term that looks like the Maxwell fisheye lens term, where R is defined over here. And this solution satisfies the Einstein field equations once you impose certain conditions on these free functions. So there's one equation, but there are three free functions here. So it's not at all clear at the outset what the meaning of these free functions A, B, and beta is. But I can see from my rewriting that beta has something to do with the effective radius of the hypersphere. Okay. So that's the Narii-Tomita solution that they introduced. The next step, the natural next step was for me to embed this model as a star in a Schwarzschild spacetime. And they didn't do that in the paper. Whether anybody else has done that, I don't at this point know. Okay, so again, we can follow the Oppenheimer-Snyder approach. Two spacetimes, interior and exterior, will match at a hypersurface if their induced metrics match and if their extrinsic curvatures match on that hypersurface. So that's the method to follow. It's only a little bit tedious to do. And we find from doing that matching at the star's surface, so here we're putting the star's surface at a radial coordinate r0 and allowing that to be a function of proper time on that surface. From doing that matching, one derives that there's relationships between these free functions A, B, and beta in the Narii-Tomita model, and the parameters of the surface of the star in Schwarzschild spacetime. So here, E0 is the energy, or the specific energy, of the surface's trajectory, and alpha 0 is the proper acceleration of the surface's trajectory. So now we have an interpretation for these parameters once the collapsing model is embedded in the Schwarzschild spacetime. Okay, with a little bit more work, we can show that beta dot, in other words, the rate of change of beta with respect to proper time, is proportional to alpha naught dot. Okay. And what that's telling us is that if the proper acceleration of the surface of the star is constant, then beta is constant too, and therefore R, the effective radius of the Maxwell fisheye, is constant as well. Or more precisely, that's telling us that the amount of the hypersphere encompassed by the interior is a constant. Okay. So now we go, now we can apply the tricks from the previous part of this talk. We make a standard coordinate transformation just as before. And now the interior geometry takes this nice hyperspherical form. If we want, we can introduce a conformal time to make that really the hypersphere there. And the dynamics has gone into the conformal factor here. Now this effective radius is the Schwarzschild coordinate of the surface of the star divided by this. And if we have constant acceleration on this star, then the extent of the hypersphere is fixed. So chi naught is fixed, and it depends on the energy, acceleration, and radius of the star in this way. And that is a fixed quantity. So the main message here is we can set up collapse scenarios so that the focusing is exactly that in a Maxwell fisheye lens, and so that in principle we can create perfect focusing if we tweak our, well, if we make things very dense. But even at more physical, more realistic values, we get lensing as if we had rays on part of a sphere. And so what I'm saying here is that we have now a wider family of collapse models with constant acceleration, and that family includes the interior Schwarzschild solution, where the acceleration is sufficient to keep the radius constant, and it also includes the Oppenheimer-Snyder collapse, where the proper acceleration is 0 and everything just falls along a radial geodesic. So we can now interpolate between those cases. So an interesting special case I'd like to look at more, I haven't actually got round to before this talk, is the case of asymptotic collapse, where we start with a sphere. Let's say we start with the Schwarzschild interior solution, but we assume we haven't got quite enough acceleration to keep it static. So we set up an acceleration that's just below that value needed to keep the sphere static. So then it begins to collapse, but we're going to keep the proper acceleration constant. What that means is that we've got a situation where our physical geometry is conformal to a static hypersphere. So we can find all our closed form solutions on the static hypersphere and then just apply the conformal symmetries to get the solution in the dynamical spacetime. And I'd like to work through that with my PhD student to get more closed form results for some interesting studies. I'll just conclude with one word of warning from a physical perspective. None of the models that I've been describing here satisfy realistic equations of state, possibly excluding Oppenheimer-Snyder, where we assume that the pressure is just 0 everywhere. But none of these models arise from equations of state. So there's something in that sense non-physical about them, but they're still interesting to many people. Okay, so I should conclude there. So the main points we've covered are that perfect focusing occurs naturally in the Maxwell fisheye lens, and the rays in that lens map to null geodesics on a hypersphere. Several well-known solutions of Einstein's field equations are conformally related to hyperspherical geometries, and these include the Friedmann spacetime in cosmology, Oppenheimer-Snyder collapse, and as described here, the interior Schwarzschild solution. Moreover, we've described today that a wider class of solutions exists. These are Nariai-Tomita stars embedded in the Schwarzschild geometry. And if the star's surface has a constant proper acceleration, then we have a fixed proportion of the Maxwell fisheye lens in the conformally related spacetime, and so we will get focusing exactly as in that system. And if you want to do some calculations, for example, for rays or fields on these spacetimes, then what I'm saying is you can go ahead and do it using the conformal symmetry to simplify calculations in many collapse scenarios. Okay, that's the end of my talk. Thank you for listening.
Okay, thank you very much, Sam, for a very interesting talk.